Okay, so this is dynamics. Yeah, this is just dynamics. I remember one of the videos I tried to introduce the same topic. We even solved one question under dynamics. But as for this one, I'll just try by all means to go in details of what actually you're supposed to know and how many things are you supposed to consider and what are those that you shouldn't be considering when it comes to calculations. So under dynamics, the first thing which you have to understand, you need to understand the laws that were discovered by Sir Isaac Newton. These laws, there are 3 of them. In that previous video, I remember I even explained each type of a law. So I'll just do a recap based on what I just talked about in that same video. So if you want to understand what the first law of motion is, I think in that same video you can understand fully, but here I'll just state it. I won't even be explaining. So the first law states that an object will remain at rest until an external force has been applied to it. The other name of this same law, we call it as a law of inertia. Yeah, that's what it explains. Then the second law of motion states that at a constant mass, the applied force is directly proportional to the acceleration and the object takes the direction of the force. That's what the second law states. Then the third law, in other ways, they call it as the law of reaction. So what does it state exactly? It states that in every action, there is an equal but opposite reaction. That's what these laws are trying to tell us. So in addition to that, what other things are we supposed to understand the most under dynamics? One, you have to know the types of surfaces. Types of surfaces. What are some of the types of surfaces? Basically, we have 2 different types of surfaces that we have to understand fully. One, we have a flat surface and an inclined surface. So these are the types of surfaces that you have to understand always. And how do you consider the forces that each object is experiencing once it rests on either of these types of surfaces? So if you want to describe how or what are some of the forces that are being exerted on an object which is just resting on a horizontal surface, or rather the flat surface. So basically, if they tell you to say this is a flat surface, what you should always understand is this. A flat surface is going to be like this. This is going to be my flat surface, meaning that an object can be resting at this given point. For this object to rest at this given part, meaning that the force it exerts on this floor is equal to the force that is being exerted by the floor. And here, this is where now we are going to understand that most of the times we are going to be using, the second and third law in our calculations. The second and third law in our calculations. These are the most laws that we are going to be applying. Now, how do they apply? What you are going to understand is, if the object is moving, for it to move, or if you are trying to push this object in a given direction, one, the thing that you should always understand is that if you are pushing the object at this given point, like this object is going to move forward. A good example, if I'm trying to push this pen forward like this, meaning that I'm applying a force at a given point whereby I'm making it move in a direction of the force. And if that asks you to say what type of what law is being applied here, definitely what you should understand is we are trying to apply the second law of motion, because the acceleration for this object to move, for it to move from this given point to where it is, or maybe to cover this given displacement, automatically you are going to use the second law of motion. So here, the first law, whenever an object is moving, we apply the second law of motion. Now, what about the forces? How do they make this object stay on the surface without it sinking into the surface? Here, this is where now we apply what we call the third law of motion. Why? Because the weight this object is exerting on this floor is equal to the force that the floor is exerting on it. That's why this object is not moving in the y-axis. We call this as our y-axis because it is just staying on the surface. Like this, if you put a pen like this, you understand that the pen is not sinking into the paper or on the surface of this entire thing. Why? Because the force it exerts on the paper is equal to the force that the paper is exerting on this one. And that's what we call the third law of motion. In every action, there is an equal but opposite reaction. So what names can you give to these types of forces, whereby the force which is exerted by the surface and the force exerted by the object? This is called a weight force. And weight, you know that it has to be equal to mg, which is mass multiplied by gravitational acceleration. This one is going to have what we call a normal force. Normal force always reacts to the applied force, which is what? The weight force. Yeah, this is the first scenario that you're going to be understanding the most. Then the second type of a surface is what we call an inclined surface. How do you consider the so-called an inclined surface? What you're going to understand is we can have this as our surface here. Initially, you can have this one, the horizontal surface. So if they ask you to say define what inclined surface is, you can define it like you just say this is a surface whereby it is oriented at a given angle. A surface which is just oriented at a given angle. What does it mean? If we have the horizontal surface like this, meaning that the object is going to rest at this given point initially. So what you're going to understand, this object is still, it is going to have what we call the weight force, I'll say mg. Then it will also have the normal force which is being exerted by the surface. So if you try to raise this surface, you do like this, you try to raise a bit at a given angle like this, what you're going to understand, this normal force, this weight force is still, it will be pointing vertically downwards. It won't change its direction. But this one, always it must be perpendicular to the surface on which the object has been placed. So a point here, I'll just say, okay, I'll say normal force must be perpendicular to the surface on which the object has been placed. And then this one should always be pointing vertically downwards. What does it mean actually if I say the weight force must always be pointing vertically downwards? If you raise this surface at a given angle, we know that even the object itself is going to be moving, but the normal force is still, it is going to be perpendicular to the surface. Why? Because you're just trying to raise this surface at a given angle, and then you can make it and come at this given part. It will maybe come at this given part, whereby the object is going to come on this given point, but still its weight force is going to be pointing vertically downwards like this. And then the normal force has to be perpendicular to the surface on which the object is resting. This now becomes the surface which has been raised at a given angle theta. Theta, we write it like this. We don't write like this at theta, or maybe theta. No, not these two, no. But this is the correct word for theta, and it is given a symbol, something like that. Now, how do you draw the same thing? What you're going to understand is the weight force initially here, it was at 90 degrees, but here it is neither perpendicular nor parallel to any of the surfaces, meaning that what you should do for you to make this one become perpendicular or parallel to the surface, which is the inclined surface, you have to resolve it into its components. We learned about vectors on how to resolve a force which has been raised at a given angle. So how do you resolve the same force which is the weight force in that scenario? What you're going to understand is this. The weight force can be written like this. So we are going to have, okay, we are going to have this as our surface. Okay, that is going to be the surface oriented at a given angle theta, like this. Then here I'll draw. Be careful on how to resolve these two things. You have to be very, very careful on how to resolve the weight force in this scenario. If you miss up a concept here, automatically you're going to be having some challenges. So weight force, I'm saying, should always be pointing vertically downwards. The weight force for this one is going to be pointing like this. I'll say mg. So since we're trying to resolve this one into its components, as it is pointing like this, it will have two different components. if you try to continue with this kind of thing, you make sure that it comes from the center of this object. What you're going to understand here is, if you resolve, it will have the first component and also the second component. Why are we trying to point this component like that and this one like that? It's because I'm trying to resolve this one. Now, how do you understand to say this is going to be the angle, or which component is going to carry cos and which component is going to carry sine? I remember I taught you how to resolve a vector. Suppose it is like this. This can be my resultant. If I'm trying to resolve this one with respect to the angle given here, you are going to understand that the x component always must be equal to r cos theta. Why? Because the same component is the one which has been cut by the angle. Same applies to this one. You say y has to be equal to r sine theta, like that. Meaning that you've resolved this one into its components. Now here we're trying to resolve this one into its components. How do you determine to say this component is going to carry cos and this one is going to carry sine? By the way, it's always that this angle which is here has to be equal to the angle at that given point. Also, this one is going to be theta. Yeah, so meaning that since this component has been cut by the angle, automatically it must be x. You say x has to be equal to, you're going to say mg cos theta. Why do you put mg cos theta? Because we are resolving the weight force. Meaning that the opposite to that is this one. You say y has to be equal to mg sine theta. In short, you can just remove this. You can just remove this because we don't exactly know. Say, okay, in this case, this is going to be my y-axis. Why? Because we're trying to point where the normal force is pointing. By the way, in this case, normal force is going to be pointing vertically. I mean, it is going to be making a 90 degrees with the surface on which the object is resting. This is going to be my normal force. Okay, now, what you're going to understand here is this. Suppose the force is moving like this one. If it is pointing like this, meaning that this is going to be my driving force, this is going to be my opposing force. This can also be drawn like this. Don't get confused here. They can even draw like this. It's the same thing. They can even draw like this. Then this is the angle, the object resting at this given point. Then its weight force pointing vertically downwards, mg, meaning that the first component is going to point like that, the other one is going to point like that. So remember, we are saying the angle between this force and what is made inside here, they must be equal to that one, meaning that this is going to be mg cos theta and this one is going to be mg sine theta. So this can also be the force, either pulling or pushing. These are the two types of scenarios that you have to be understanding the most. How to scratch. Okay, so this is the second thing which you have to know also. We have this one as the first thing and this one be the second thing. So here, what you should always understand, I'll write a point here to say either pushing or pulling. The force must always be pointing away from the object. Meaning that if they would say, I was pushing this object with a given force of blah, 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 blah. What you should always understand, you don't put like this. I know that this is going to be mg, then this is going to point upward as a normal force. If you are pushing this object at a given point, you shouldn't be indicating the force like this. You have to make sure that the force which you are using should always be moving away from where? From the object. If there is an opposing force, which is a friction force, should also be pointing away from the object. This is going to be F and this is going to be friction, like this. Yeah, so that's how you have to be describing this to my simple stuff. And how do you take the same forces? Always the force which is making the system move, or rather the object move, must carry what we call a positive acceleration. The one which is trying to oppose, it has to carry a negative acceleration. Why do you say these are the scenarios that you have to be considering? It's because if this one is moving forward, then the other one is trying to oppose. It's more like this is moving towards the positive, this one is moving towards the negative. Even if the driving force is pointing towards the negative, still we are going to consider it as a force which is moving towards the positive side of the entire system. And how do you calculate? Following the second law of motion, since we have two different forces in this scenario, what you should always do, you should make sure that you know how friction force is related to these other forces. What is the relationship between friction and the normal force, including this one? How do you describe it? Before you do that, you have to understand also to say what are the types of friction force that we normally consider when it comes to calculating equations based on dynamics. So first of all, you have to know the types of friction forces. So we have two different types of friction forces. The first one we call it kinetic friction and static friction. How is friction force related to these remaining forces? Friction force can only be related to normal force using what we call the coefficient of friction. How do you describe the same coefficient of friction? Coefficient of friction is the ratio of a friction force to the normal force. Like this. So if you are able to understand these simple terms like coefficient of friction, normal force, and friction force, you can even relate them based on this system same statement. What symbol is given to the coefficient of friction? This is given with the symbol mu, like this. So this mu is written with this comma symbol as you're trying to write u. And then this u, which is mu, it depends on what type of friction are you having. If you're having friction as a kinetic friction, you have to put a k here, meaning that even this one is going to carry what? Is going to carry mu k. If you are having static friction, you are going to write like this, s. Even this one is going to have s like this. Now, how is the friction force related to the so-called normal force? What you're going to understand, we are saying coefficient of friction, it must be equal to the friction force or ratio of a friction force to the normal force. This shows that friction force in this case must be equal to mu normal. So in this relationship, you find that it becomes something which is very difficult for you to understand what normal force is going to be equal to. But it is very simple for you to understand what normal force it must be equal to. What you should always understand is this. We are saying normal force, it must be perpendicular to the surface on which the object has been placed. Meaning that on the horizontal surface like this one, if you have, this is my weight force, which is mg, this one is going to be my normal force n. Even if this object is going to be moving, if it is moving pointing like this, meaning that there is acceleration, the forward force is going to be applied force. If there is a force which is trying to oppose this, it is called a friction force or air resistance, whichever. So the direction taken by the object, we call it has taken the direction of acceleration. So since the object only moves in the x-axis, it is not moving in y-axis, what you should always understand is this, meaning that in the y-axis, the summation of these two forces must be equal to 0. And then the summation of these two forces, it has to be equal to what? Acceleration. So I said the force which is pulling the object or pushing the object, it must carry what we call a positive acceleration. This one is going to carry a negative acceleration. Same applies even here. Since this force is moving upward, we call it as a positive force. This one is going to have a negative force. Then when it comes to summing up these forces, what you should always write is this. You are going to write it like this. You say, since it is moving in the x-axis, meaning that you are going to take this one which is having a positive acceleration first of all. The meaning of summation of forces in x must be equal to acceleration. That's how we write acceleration, because mass multiplied by acceleration gives us the force that is making the system move. So since we have two different forces in the x-axis, you say the force which is making the system move plus this one. So since this is trying to oppose, it must carry a negative. We say minus friction, you are going to get ma. You come in the y-axis. This object is not moving in the y-axis, meaning that you are going to write it like this. You say the summation of forces in y must be equal to 0. Why don't we include acceleration? Is because the object is just resting on the surface, meaning that the upward force is equal to the downward force. In this case, you say the force which is moving up as a normal force. In this case, you write it as part of the positive force. Then you say plus the one which is having a negative, it is trying to oppose mg. You're going to equate everything to 0. That's why on the horizontal surface, if the object is moving or it is not moving, still the normal force has to be equal to mg. That is if a force is being applied in that given direction. Now, there are cases again, you find that this force can be raised at a given angle. How do you consider the same normal force if the force has been raised at a given angle? Either pushing at a given angle or pulling at a given angle. How do you consider the same normal force? So we are going to have the first type of a scenario. We can have this. The object is resting at a given angle like this. Then you are trying to pull it. You are pulling this object with a force at that given point. We know that this force has been raised at a given angle, which is the angle with respect to the horizontal. This one which is given at that given point. Now, how are we supposed to be considering the same scenario? What are some of external forces that acts on this object? One, you have to understand that this object is having the weight force. It is also having what we call the normal force. Look at where or at what direction the normal force is trying to point. Meaning that for you to understand what will be the driving force for this one, I won't consider this one, but I'll take the force which is making the entire system move forward. Meaning that this force which has been raised at a given angle, it must be resolved into its components. How are you supposed to resolve this? We learned about vectors like what I'm doing here. This is how we resolve. So this acts as the force, meaning that this is going to be your x-axis. Why? Because we are looking at what angle is cutting the axis. This is going to be f cos theta. Then this one is going to be f sine theta. Now look, we have two different forces pointing upwards. The component for this force and also the normal force. Meaning that even if there is another force which is trying to oppose, like friction force, still this is going to act as the driving force now, this one, because that is the force which is moving forward. This one cannot move forward. Why? Because it is raised at a given angle. So what you should always do here is this. For you to understand what would be the normal force in this case, in this scenario, in a pulling force, remember we are trying to resolve the vectors from the tail. We don't resolve a vector from the head, no. We resolve it from the tail. Meaning that you say the summation of forces in y must be equal to 0. We are equating everything to 0 because the system is not moving in the y-axis. So here what you are going to do is this. You say, since we have two different forces pointing up, that's what it means when you say summation in y-axis. These two, they are all going to carry a positive acceleration, or rather I will say a positive acceleration. Yeah, this one is going to have a negative acceleration, meaning that you say normal plus the component which is also pointing upwards, sine theta, minus the one which is trying to move downwards, mg. It has to give us 0. So if you try to take normal plus f sine theta, equate everything to mg, what you are going to understand is this. We are going to have n giving us, this can now move to the other side. We are going to have mg minus f sine theta. This is how we consider a normal force in a case whereby the force has been raised at a given angle. Okay, that is according to the first scenario. The second scenario is when you are pushing the object at a given angle. How do you consider the same normal force? Suppose you are pushing this object at that given point. You are pushing this object at this given point. I know that it must also have an angle like this one. Since you are pushing, this becomes the tail, this becomes the head. Meaning that the angle which is made here, it is made along the x-axis. Then if you try to cut this like this, what you're going to understand, we are making the alternating angle like this. We are making the alternating angle like this, meaning that we are going to have the first component pointing like this, having the same angle as this one. Even here we're going to have theta. We learned about this from grade 7. Then here we're also going to have another force which is going to be pointing upwards. You don't resolve this one like you point here and then you point up. No, you follow the direction taken by this one. It must lie between the two components. This acts as the resultant of two different components. That's how we do resolve these two simple things. Okay, so this is going to be F cos theta, and this is going to be F sin theta, meaning that the normal force is going to point like this, and the weight force here is going to point downwards. How do you consider now the same forces now in y-axis? You say summation of forces in y-axis must be equal to 0. So what you're going to do here, we have this and that, and also there is another component which is trying to point downwards, meaning that the summation of upward forces must be equal to the summation of downward forces. So you say normal minus one of the components pointing downwards, mg minus f sin theta, giving us 0. If you take these two to the right hand side, you are going to understand that normal force in this case, N, is going to be equal to mg plus f sin theta. If you check, this is for pulling force at an angle. This one is for pushing force at an angle. There is a difference. For pulling, we have a minus in the middle. For pushing, we have a plus in the middle. That's the only difference which is there. Why do we say there is a plus? Because this component for this one, this component and that one, they all point vertically downwards. Yeah, so if they ask you to say, can you draw the free body diagram? First of all, you need to understand a free body diagram. This is just an illustration or a diagram which shows all the forces, or rather external forces, that acts on a given object. Okay, now away from that, what you should also understand, we have a different type of question, or maybe I would like to say we have also a different type of questions that are also calculated under dynamics. These questions, they require us to have a full understanding of what we call Atwood's machines. It requires us to have a full understanding of what we call Atwood's machines. Now, what are the same Atwood's machines? Atwood machine, this is a connection of two different objects using a string over a body. So we have so many types of Atwood's machines. We have so many types of Atwood's machines. But before I do that, what you should always understand is this. If I'm trying to get just a bit back to what we call the inclined plane, you are going to understand that people normally face a lot of challenges when it comes to resolving the force, which is mg. This mg should always be, in this scenario, normal force is not equal to mg. Why? Because it is pointing in that given direction. In this scenario, meaning that normal force N is going to be equal to what? The component of mg, which is going to be mg cos theta, like this. That's how we do consider the same normal force. Then for this one, same applies even this one, since it is having a similar diagram to the one which is on top. Even here, normal force pointing like that, still it is going to have the same type of a thing. Now, in this diagram, we know that if they ask you to say, can you draw a free body diagram for a scenario whereby they even give you maybe the coefficient of kinetic friction, coefficient of static friction, how are you supposed to handle the same question? What you should always understand is this. On this diagram, let me put it on top a bit. On this diagram, we are going to have this object. If we have the applied force in this given point, then we have an opposing force, friction. We have normal, mg. We also have the force pointing upwards, normal. What you should always do here is, first of all, you say the summation of forces in x must be equal to acceleration. Why? Because this one is going to point that given direction, meaning that the type of friction they're going to consider, or we're going to consider here, has to be kinetic friction. Why? Because the object is moving with a given force. But since this force is greater than that one, this is going to have a kinetic friction. The friction force is going to be there, but it will be less than this one. Again, there are cases whereby you find the object is going to be at rest without even moving. What exactly makes it not move is the what we call friction force. The name given to that type of a friction force is what we call static friction. Static, the meaning of static means that the object is not moving. So if you say the summation of forces in x-axis has to be equal to ma, that is if the object is moving. If you say the summation of forces in x has to be equal to 0, meaning that the static friction is greater than this one, the object is not moving in that same case. So what you're going to understand here is we're going to have the summation of friction force giving us that, meaning that we have two different forces. I said the force which is making the system move, it must always have a positive sign. This one is going to have the negative sign. Why? Because it is opposing. So you say the forward force F minus friction, we're going to get M. Even on the Atwood's machines, still we are going to be using the same things, but I'll show you how to go about that. Then in the y-axis, don't even worry, the object is not moving in the y-axis. Definitely what you're going to do, you just say the summation of forces in y must be equal to 0. Then you're going to have normal minus mg, equate this to 0, and the normal force in this case is going to be equal to mg. Okay, so remember I said friction force is equal to mu normal. Normal force, we're saying on the flat surface, normal force has to be equal to this. Why? Because the object is not moving. And you need to make sure that this force is pointing in that given direction. That's when you can say normal force is equal to that. If it is raised at a given angle, you know what to do. Normal force can't be equal to the mg. Why? Because we're going to have a given component for that same force which is raised at a given angle in that same scenario. So since normal force is equal to this, and you put this as either kinetic or static depending on the type of a friction we are having. So since the object is said to be moving, acceleration pointing in that given direction, this is going to be k, this one is going to be k. We are saying normal force must be equal to what? Mg, meaning that friction force k has to be equal to mu k mg. This is what we're going to take and replace where there is what? Where there is friction force in the expression. So we're going to have something like this now. You say the driving force, or rather the applied force, minus mu k mg, giving us ma. I solved one of the questions in the previous video. If you didn't watch that video, please try to get back to it and you'll be able to understand. Alright, now this is how we have to be considering this same thing. We are done on this part. I won't solve any question. I'll just explain everything since we solved some of the questions already. Okay, so Atwood's machines. This is Atwood's machines, not art, the art you are learning anyway. Not this art, no. But Atwood's machine. Atwood machine, if you are to define it, this is a connection of objects using a string over a pulley. So the Atwood's machines, there is at least we have two different types of these same Atwood's machines. We have a pure, and then we also have impure and the like, but those are not even important to your part. What is very, very important is to understand what this concept is all about. Now, we try to look at what exactly are some of the diagrams that requires us to have a full understanding under Atwood's machines. So the first diagram is the one which requires us to have an understanding of what we call pulley system. We can have this. Like this is the first system. You can also have pulley here, then we're going to have the object here, then the other one is going to be hanging like this. We also have another type of this one, which is in a form of this one. We're going to have a pulley here, a string can go up there, then the other object is going to come somewhere there. We can also have the other type of these same pulley systems. Just a bit. This one comes. Okay, the other type of a pulley system is the one which is having something like this. Then we can have a pulley at this given point like this, then a string passing through that, then something like this. That is the other one. The last one is when you're having a table like thing, then you have the object in the middle, you also have the other object here, you also have another object somewhere there, then you have a string connecting these, then we also have a pulley pointing at this given point. So these are the things that you have to understand the most. As for me, I'll just consider first of all this and that one. The remaining ones we are going to learn them physically once we land on the campus. Okay, what are you supposed to understand here? What you're going to understand the most is, for this system to be said to be accelerating, it depends on what masses you are having. It depends on what masses you are having. If the mass of this one is greater than this one, automatically this mass is going to make the entire system move. Meaning that this actually means that if you have something like this, right? You have, suppose we have this kind of thing which is less than this one, like this. What you're going to understand here is this. Since this one is greater than this one, we can just put maybe 5 kg, 2 kg. For you to understand what direction these two are going to take, this one is going to make the entire system move downwards. It will move downwards. This one is going to move upwards. Why? Because these two, they are connected to the same string. The tension in the string, it becomes the same. Why? Because they are all connected to the same tension. So the tension is going just to be the same. In fact, including the acceleration itself, it will also be the same. Why? Because the acceleration this one is going to have will be equal to the acceleration for this one. Before you even start calculating, what are you supposed to do? You have to understand how to draw what we call free body diagrams. Free body diagrams. The meaning of drawing a free body diagram, actually it means you have to separate these two into their forces that acts on each. I understand that this one is going to have two different forces. Even this one here, we don't have x-axis, we only have the y-axis. How do you consider the same forces in the y-axis? What you should always do is this. You have to separate this tension into two. We are going to have the first one and also the second one. This one, which is a 5 kg mass, you can label it as M2. This one, it is going to be labeled as M1. Still, here, the second law of motion applies. Second law. Why? Because these two are objects that are going to be moving now. Second law of motion has to apply here for Sir Isaac Newton. So, since I've separated these two into different diagrams, what you should always understand, we are saying the force the force acting on the object should always be pointing away from the object, meaning that here tension is going to point like this. Even this one, its tension is going to point like that. So since here the tension is the one which makes this object move, but here it's not the tension which makes this system move, it's due to its mass, or rather the weight of this one. That's why it points vertically downwards. For this one, it's the tension which is trying to make it move upwards. Though there is weight force, mg, which is m1g, this one is going to have m2g, J like this. Still, what you should know is these forces, they have a specific thing which makes them move. Here we are saying the weight force is the one which makes this one move. Here we are saying tension is the one which makes it this one move. Meaning that tension is going to have a positive side. This one is going to have a negative side. Here, this is going to have a positive side. This one is going to have a negative side. I'll say T and also T. How do you write? Just write like this. You say summation of forces in Y must be equal to MA. Why? Because the object now is going to be moving in Y-axis due to the movement of either of the two ones that you release them. So, you want to write for this one. Since the tension is the one which makes this move upwards, what are you supposed to do? You write tension on the right hand side. I mean, on the first part, you say T. Then the one which is trying to oppose moving downwards, since this is pointing up, this is pointing down due to their illustrations. Always the force which is greater than the other, it must make the system move. So we are going to have T minus the downward force. I'll say minus M1 G. You equate everything to acceleration. What name is going to be given to this mass? Remember I said since this and that they're connected to the same tension, which is TT, they're going to have the same acceleration. No need of saying T1, I mean A1, A2, no. But what is going to differ are masses. You label it as M1A. You come to this one. What you're going to do, you say the summation of forces in Y must be equal to MA. Look at what force makes the entire system move. Here is due to this weight. The weight of this one is the one which makes it, everything move. So you are going to put the same M2G on the first part. Then the one which is trying to oppose, this one is less than that. And then here, this one is greater than that. That's why we start with the greater force, ending with the one which is trying to oppose. So you say minus T. Then what name is going to be given to that mass? You say M2A. Then you say this is going to be your first equation, this is going to be your second equation. What are you supposed to do here? You say add 1 and 2. How do you add? Just get this equation and then you add with that one. You can either use elimination method or substitution method. So I'll say T minus M1G giving us M1A. Now say M2G minus T giving us M2A. If you try to add, what you're going to understand, since this is having a positive, this is going to have a negative, this and that, you can just cancel them. Then you are going to add the one which is having a plus first, M2G, you come to that one, M1G giving us M1A plus M2A. What are you supposed to do next here? What you should always understand, you can just factor out what is common. I'll say G, open, M2, M1, A, M1, M2. You divide by M1, M2 over M1, M2. Meaning that acceleration can only be calculated by the formula which is M2, M1 over M1 plus M2. Simple. This is the formula that you can use to calculate for acceleration. A question might come to say, can you show that acceleration is equal to this? They automatically mean you have to take this entire process. If you have been asked a question like this, even if they haven't mentioned something like you have to draw a free body diagram, the first thing, draw a free body diagram. If you haven't drawn, you are losing your marks. That is well clear. You try to go to the second type of a pulley. I said I also concentrate on this one as the second type of a pulley, which is like this. Even if the mass here, this mass can be less than that, but still it will make this move. How possible is that? It can only make this one move if this surface is smooth. If the surface is not smooth, it can't make this one move. But in this case, I'll take this one to be maybe 5 kg again. Then this one is going to be 2 kgs. So this will be my M1, M2. If friction force is there, it must point in that given direction. You say friction force. If it is not there, then you forget about it. So remember, I'm saying always a force must point away from the object. you have to draw first of all the free body diagrams for this and that one. So I'll start with the one which is on the horizontal surface. Remember, the force which makes it move forward, we call it as a tension force since it is pointing away. Then the one which is trying to oppose, it has to be named as the friction force. This must have an mg and the normal force pointing in that given direction. Why? Because it is resting on the surface. This is my surface. Then this also is my surface like this. But since this one is hanging, it will only have the forces in the y-axis. Then this is going to be moving. Even this one is going to move. So I'll draw the free body diagram for this one. Look at the way I'm drawing the free body diagrams. Separately, you draw them clearly. So we are going to have M2 here. This has to be M1. So tension has to point away. What force makes this one move downwards? I know that this is going to be moving in that direction. This one is going to be moving in that given direction. Meaning that here you say the summation of forces in x-axis has to be equal to acceleration. Why? Because this one is resting on the surface like we did in that other diagram. So here we're going to have M2G. Two forces only that acts in the y-axis, making this one move in that direction. Then this one is going to be moving in that given direction. So what you should do here, you just say for this one, you say summation of forces in x must be equal to m. What is this mass? The first mass, which is 2 kgs. So you say tension minus friction, it has to give us m1a. Why do I write like this? Because tension force is the one which makes this object move. For this one, you say the summation of forces in y must be equal to ma. Why do I write in y? Because this one is moving in the y-axis. It is not moving in the x-axis. So we are going to have m2g minus t giving us ma. So what you're going to understand, remember we are saying the friction force for the object which is resting or maybe moving on the horizontal surface, friction force must always be equal to mu mg. The mg is what we call the normal force because the object is not moving in in y-axis. All right. So if you add, this becomes my second, this becomes my first equation. If you try to add this and that, what you are going to understand, we are going to have T minus friction equal to M1A. Okay, then we are going to have M2G minus T equal to M2, put 2 there, A. This and that will be cancelled also. We are going to have M2G minus friction giving us M1A plus M2A. But remember what this one is all about. What are you supposed to put here? You have to put the one which I'm from showing on top there. This one. That's what we are going to replace where there is friction. So we are going to have M2G minus mu. This mu depends on what a type of friction you are having. If the object is moving, that is coefficient of kinetic friction. So we're going to have mg equal to m1 plus m2. I have factored out a like this. Even here you can factor out g. We're going to have g open m2 minus mu m1 equal to m1 m2 a. You divide by m1 plus m2, also here m1 plus m2 like this, meaning that acceleration has to be equal to g open m2 minus mu m1, you close, over m1 plus m2. They don't only ask for acceleration, they can also, even for this one, they can even tell you to say, can you find the tension for this one? Meaning that for tension, just pick whichever equation, either this one or this one. Then you have all the values. Since we found the acceleration using this formula, you can just replace where there is acceleration. You make this one move here. This one is going to come to the other side. Then for this one, you just make this one move to the right hand side and you'll be able to find it, the value for the tension. Same applies even here. You can either use this one or you can use that one. Still the tension is going to be the same. Why? Because it acts as the internal force. Here it must move upward, here it will be pointing in that given direction. So this must be the end of this illustration. The questions that I'm going to post in the group, you can try to solve and so on. Thank you for watching.